Okay, in this video I'm going to talk about where that equilibrium constant that we've been using in these other videos actually comes from. It is actually related to the rate of reaction, and if we recall the rate law, if we say that something is the rate limiting step, then we would say that if we had the coefficient of A acting on X and the coefficient of B on Y, and we were going to say that this was the rate limiting step, then we would say that the rate of this reaction was proportional to X to the power A and Y to the power B. So you can go all the way back and see a much earlier video discussing the rate limiting step and reaction mechanisms and its relationship to all this. But basically this is the idea. So then this proportionality, I guess, means that we can say equal as long as we put in some sort of coefficient. I'll use a little k here. Actually, I'm going to change that because that might be a little confusing. Let's use the coefficient c so that it's not the same as k so we don't get confused. Now, if we consider the overall reaction, A with X and B with Y, going to, I'm not going to use C because I just used it, so D to W and E to Z. Then at equilibrium, what we say is the rate of the forward reaction is the same as the rate of the backwards reaction. So the rate of the forward should be equal to X to the power A and Y to the power B. Here, unlike with reaction rates, we don't need to use the rate limiting step because for this reaction to go full circle, to go all the way to one side and all the way back, all of the products need to be used up, so we can use the overall reaction here, not the rate limiting step, which is a lot easier. Don't forget our constant C. I'll call it C1 or CF for forward, it doesn't matter. And then my rate for my backward reaction, again, I can use the overall reaction to come up with this rate, even though it isn't the rate limiting step necessarily, because this reaction has to go all the way to completion before it can turn around and come back. So all of the materials need to be used. Now I can take these two things and I can set them equal to each other, so at equilibrium. The forward reaction rate is equal to the backward reaction rate. So C X to the A and Y to the B is equal to, so that's C forward, C of the reverse or backwards, W to the D, Z to the E. Now we're going to set this up in a specific way. We're going to bring all of our constants over to this side and all of our variable stuff over to this side. So now it really depends on what the nature of these reactants were. Let's just play a game here. Let's make this a gas. Let's make this a solid, this a gas, and this a gas. What that would mean then is that this gas is variable, this gas is variable, and this gas is variable. So they're all going to go to the right-hand side. So that's W to the D, Z to the E, that's a D. And what else was my gas? My A to the X, or X to the A. And if I bring my X over here, and then I'm going to bring all my constant stuff to this side, so CF divided by CB, and my Y to the power B, because it's a constant, would stay here. It's a solid, so that means it has a constant concentration. Recall from a previous video that constant concentrations are things that are solids or liquids. Gases or aqueous products have variable concentrations. So I'm going to take all this constant stuff because it doesn't change, and I'm going to turn it into one giant constant, and I'm going to call that the equilibrium constant. And that's going to be equal to the concentration of my products over my reactants, as long as I'm only including variable concentrations. Again, gases or aqueous products. So this expression that we talked about in previous videos really comes from the idea of setting the forward and reverse reaction rates equal to each other based on the rate laws, excluding constant items to come up with the simplest equation that we can come up with that is constant except for all of the variable concentration issues or particles. So that is where we got the equilibrium constant from.